Hello, everybody.
Hello.
Hello, Professor.
Hello, sir.
Hi, Professor.
Let's go to wait a few 1 minutes more to people to enter to the meeting.
Hey, Professor, I had one question. In any way, will you be accepting past due homework before the end of the semester?
Uh, yes, I think yes. I will accept any late homework. If you have any homework, you let me know and I will reopen, okay?
Thank you.
So this is today class. We have to rush a little bit to end the last chapter that we have to study about rotation. And so I would like to make this class today a little bit different. Please let me make what I think that I have to make in 1 hour, and after 1 hour I will discuss with you all kind of doubts, all kind of questions, and you know that you will have today the quiz. Quiz 6 is the last quiz that you have to take. And remember that you have test 2. I will tell you in 1 hour how is the test 2. The test 2, well, I will tell you very quickly. Meanwhile, the people there are 37 people only here now. Where are the other people? Wow, 37. Do we wait a little bit for more?
Professor, I have a question.
Yes.
I was one of the students that took quiz 5 from 4 to 6.
Ryan.
Yeah.
Let me class and we will talk about this after I finish the class. I want to be sure that we don't spend too much time with another thing. So after I finish the class, we start to review everything. I will answering you all kind of questions. So let me share my screen. Let me share this my iPod screen and we start. Okay, we start. Just a moment. I will answer you all kind of questions. But first, let me be sure that this class is done because it's the last class. So I don't have any other option to recover this class. So this is the last class. Okay, so what we have seen is the following one. The first thing that we have seen, we are going to review a little bit what we have seen until the moment, and also we are going to see how to apply Newton's law for a rotation of an object. So this is the most important part of this chapter, and I want to be sure that we use examples so you can catch the idea and make the homework that I will ask you to make. That will be very similar to the problems that you will find in the test too. Okay. So the first thing that we have study is that when there is a rotation, there is a change in the angle, and the change in the angle per unit of time is what we call the angular velocity. So the angular velocity is the change in the angle per unit of time. So the object is rotating, every body is rotating from P to P prime, is covering an angle, delta theta, and the time that takes the angle to cover this angle delta theta is the angular velocity, We saw also that the relation between the linear velocity and the angular velocity, the relation between this velocity, the velocity tangent, when you make this is the axis of rotation, the object is rotating around a circle. So the relation between the linear velocity and the angular velocity is that the linear velocity is proportional to the radius, is omega by r. We also saw that the tangential acceleration is the angular acceleration by the radius. These things you are going to use a lot of in problems, and we will see a lot of problems that you are in need to use this kind of relation. Also, what we have seen, we have defined the kinetic energy of a solid object that is rotating around an axis, and we have got the relation that the kinetic energy of an object that is rotating with certain angular velocity, the kinetic energy is 1/2 of the moment of the inertial moment by omega squared. So this equation you will use a lot also. So you have to get used to know this kind of equation. The other thing that we have defined is the angular momentum. The angular momentum, remember, was defined like L equal R cross P or R cross NB, and we define the magnitude of the angular momentum as R MP by of the angle that they form the position and the velocity. So position and velocity is makes an angle, and the angular momentum is defined by this equation. And what we have seen that for us object that is a rigid object, the relation that takes place from the angular momentum is that the angular momentum is proportional to the angular velocity. Also, we saw in the last class that the torque acting on an object is defined like R cross F. And I think that here is where we end it. I think that we didn't see this equation, right? Or we saw this equation last time.
No, we didn't see it.
We didn't see. So let's go to start from here. So let's go to derive this equation. What it means, this equation. It means you sum all the torque as a vector, of course. All the torque, and the sum of all the torque is the moment of inertia by the angular acceleration. So I want to deduce this equation. So imagine that this is the axis of rotation. Imagine that you have an object. Imagine that the object is a disk. So the disk, just a moment, please. Just a moment. Just a moment. Okay, so we are going to derive this equation, the sum of all the external torque, the sum of all the external torques is the moment of inertia by the angular acceleration. So imagine you have an object. Let's go to draw as a disk. So it's a solid disk. Let's say that I fix my axis of rotation through the center of mass of the object. So this is the axis that is going to your eyes. The object is rotating through this axis. And why can you move? It's moving because there is a force acting on the object. There is a force acting on the solid object. So this force can be like this, or can be tangential, or maybe can be like this. But the force that will rotate the object is the tangential force. The force that create angular acceleration is the tangential force. This force will not create any rotation. So you can see in this way that the torque is involved in this calculation. So let's go to see how we involve the torque. Let's say that the force make a displacement delta S. So this is the circle, this is the axis, this is the force F. So an F tangential, always the force is tangential to the solid. So the torque, the magnitude of the torque is the magnitude of R by the magnitude of the force by the sine of the angle. But F by sine of the angle, what is that? F by sine of the angle is the which force?
Tangential.
The tangential force, correct. So the magnitude of the torque is R by the force tangential. But a force that is tangential to the path, what is doing? Basically, what it's doing is to change the velocity per unit of time. So what it's doing is that is R by M by the change, but the change in the vector velocity or the change in something different. The force is acting on the solid, and the tangential force, what it's doing is changing the magnitude of the velocity. So indeed, what we have to write is that the torque is R by M by the change in the magnitude of the velocity per unit of time. So this torque will be R by M by the change in the velocity. The change in the velocity is V final minus V initial divided by delta T. Oh, this will be R by M, but V final is omega final by R. Because you know that we saw here that V is omega by R. But this omega is omega final. Why omega final? Because the force is creating angular acceleration. So should be omega final minus V initial. V initial is omega initial by R divided by delta T. So the torque, the magnitude of the torque will be R by M by R common factor, omega final minus omega initial divided by delta T. And what is omega final minus omega initial divided by delta T? What is? What?
Angular acceleration.
The angular acceleration is the change in the angular velocity per unit of time. This is alpha. This will be R by M. Sorry. This R is the same as this R. Okay, sorry that I have used two different R. Okay, will be, sorry. Let's use it R, not capital one. Let's use it the other R, small r. Sorry. Let me prepare this. So is R here, is R here, is R here, and here is M R squared. So there is something that I forgot. M R squared by alpha. Do you agree?
Yes.
Yes, okay. So this is the torque that is applied to the mass M. If I apply the same torque to all the mass M sub I of the solid, the torque, the total torque will be the sum of M sub I R sub I squared by alpha. So will be I by alpha. So we have proof, because this sum is the moment of inertia. So we have proved that the magnitude of the torque is proportional to the angular acceleration. This is very, very, very similar as Newton's law when you write that the force, the magnitude of the force is equal to mass by the magnitude of the acceleration. Only that in this case, the mass is the inertia. The linear acceleration is the angular acceleration, and the force is the torque. So in rotation, we don't use the force, we use the torque, because the torque creates rotation. In rotation, we don't use the mass of the particle, we use the inertia of the particle, because the inertia is the quantity that describes what is happening to the. And in rotation, we don't use the linear acceleration, we use the angular acceleration. So this is the equation that is similar to Newton's law for a particle that doesn't rotate. A particle is a point, and a point cannot rotate. But if the object is like this, the object can rotate through an axis. So the Newton's law that we will apply is that the sum of all the torque acting on the object will be I by alpha. So if you see something with angular acceleration, it's because here there is a torque that is not zero. But if you see a solid, an object that is moving with acceleration, you can say that the acceleration is produced not only by a force, it's produced by a torque. So if alpha is equal 0, this means that the torque, the sum of all the torque is 0. If alpha is not 0, is accelerating, is because there are torque acting on the object. And the torque produces acceleration. So with this, we have proved this part. Okay? We have proved this part. Now let's go to prove this part, and we are done to make problems. And I have prepared several key examples that if you know how to solve this key example, you will know how to solve any problem that they can make you to do, any problem that they propose you to do, you will be able to do it. So let's go to derive the second equation. The second equation, so we have derived this equation, right? I think because I will not have time to upload videos for this part from here to Thursday. I think I will not have time. I consider that the class is being recording on Zoom. I'm going to post this class on Zoom, And my advice is that you review again the examples that we are going to solve. You review it again carefully. You see all the details because a problem similar like this you will find on the exam, on the test too. So it's very important that you review this class directly on Zoom, okay? So let's go to get another connection. Another connection. Another connection is like this. The force is the change in momentum per unit of time. This is the average force. Is mv final minus mv initial. This is the momentum divided by delta t, or m by v final minus v initial divided by delta t, or what you know, m by a. This is the force. In rotational movement, we have a similar equation. And the similar equations say like this. The force is translated to the torque in rotational motion. And can you tell me the linear momentum for what it is the similarity object that I have to use?
Wait, ask that question again, Professor.
Question is, for torque, I will not, for rotational movement, I will not use force, linear force. I will use torque. And what I will use here? I will use change in angular momentum per unit of time. So this is the question that I want to discuss with you, that the torque is the change in the angular momentum per unit of time. Okay? This is what we are going to see. And this is valid when delta t is very small. When delta t is very small, the instantaneous torque is valid. But let's go to see the derivation of this. So remember that L is, let's go to do something else. Let's go to do something else. Imagine that you have this problem. What is the area that is here?
The length times the width, or A times B.
A times B. Now imagine that you change A in delta A, and you change B in delta B. Now the area will be, the new B will be B plus delta B. And the new A will be A plus delta A. So the new area will be bigger. Is correct or not? And what is the change in the area? Geometrically speaking, the change in the area is basically here and here. Do you agree with me?
Yes.
Yes or no?
I just don't know where you're getting, like, are you increasing the size of the box? Like,
Yes, suppose that I increase the size of the square, of the rectangle by a certain quantity delta A. Am I increasing the size of B of the rectangle by a certain quantity delta B? So the area will be increased, and this is the change in the area. So the change in the area is here. So what will be the change in the area? The change in the area is the change with the area that is here and the area that is here. The area that is here is B is A by delta B. A by delta B. And the area that is here, can you tell me, is B by delta A. Correct? And the chain is also here. This is small square. What is the area here? The area here is delta A by delta B. Let's go to put it. Do you agree with this?
Yeah, I see it.
Okay, good. So the chain in the area is the chain in A by B. So if you remember, the triangle operation is the chain in A by B plus B by the chain in A. This is the triangle operation, it's the same thing. Okay, the chain in A by B plus B by the chain in A. So with changes, it happen this kind of things. So let's go to make a change. Let's go to make another chain that is a little bit more complicated. Let's say that you have LR cross B. Or let's say that we put R cross MB. What is the chain in L? The chain in L will be the chain in the first one by the second not being touched plus the first not being touched by the chain in the second. Do you agree? I'm just copying this equation. I just copying this prescription. The prescription say that when you are going to make the chain of two variables, you make the chain of the first and you multiply by the second, clean the second without touching, and you make, sorry, I did it wrong here. Sorry. I copied wrong. Sorry, just a moment. B by delta A, okay? A by delta B. Sorry that I did it. Let me erase here. I'm sorry that I'm wasting time here erasing this. Okay. So,
It's okay, Professor. Take your time.
okay. So is the chain of the first by the second plus the chain of the second by the first. This is the change. Plus this small thing. But this change is very small, as you can see. So I can depreciate. If delta A is very small and delta V is very small, delta A by delta V will be even smaller. So I can depreciate. The big changes on the area are here. So when I do the chain in L, in the angular momentum, I make the chain of the first by the second MB, plus the first not being chained by the chain in the second. Do you agree with me that this is something that has sense? So let's go to divide this equation by delta t. So will be the chain in the first divided by delta t cross MB plus the second cross product by the chain MB divided by delta t. Is correct? Yes or no?
So you're saying that, so all of the x's are cross product, right?
Mhm.
Okay.
Is correct, of course, is correct. So the chaining out per unit of time is what is the change in position per unit of time? What is the change in position per unit of time? V, the velocity, plus R cross, what is the change in momentum P per unit of time?
Displacement.
The change in momentum per unit of time is the force. I have put it here. The force is the change in momentum. Sorry. The force is the change in momentum per unit of time. And I have proved it. This is mass by acceleration. I have proved it that before, okay? So, any details, you go and you rewind the video and you will discover what is missing. For sure, you will discover. So can
But
you,
you said you're not putting up videos for what you're teaching right now.
sorry,
You said you're not putting up videos for this right now.
not for this part. I'm sorry, not for this part because I'm afraid that I will arrive too late for you. And the test 2 is on Thursday. So if I'm not lucky to upload today, I'm uploading tomorrow afternoon, it will be too late for you. So I'll better tell you at once, please review these lectures again to check all the details, to be sure that you don't miss any of the detail that is on this lecture, okay? So,
You realize that, Professor, that makes it a lot more difficult for us because we're 2 days away from the test, and you're telling us now that you're not going to upload the videos because you didn't have enough time, and now that we're going to have to be required to go back to the lectures and find out the details. It does make this a little bit more difficult for us.
Diego, only to this lecture, only to this one. Just to be sure that you didn't miss any, because what happened is that when I make the video, I make possible that you don't miss any detail because I do it step by step. I review on the videos, I review the class, and I do it step by step. Now I'm trying to do the same thing that I was going to do later. I'm trying to, but just during the class, just using this class to do this, to do all the details. So in this way, I don't have to invest so much time to create again all the videos and uploading. It's a hard work to upload all the videos, to put it one by one. It's really, believe me, it takes so many hours that I'm afraid I will not have this time. So for you, it's the same. The difference is that instead of having the unit 6 section by section, you will have all together in one class. But for you, it's exactly the same thing. So just what I'm asking you is please review this class. Don't wait for a video that I should have upload. Just review this class. It will be similar as the video that I'm going to upload. Okay. So can anyone tell me what is V cross V? Can anyone tell me what is V cross V? Well, V cross V is the magnitude of V by the magnitude of V by the sine of the angle that they form, that is the sine of 0. So V cross V is V squared by 0. So it's 0. So the vector V doesn't make any rotation on V. Okay, V cross V is 0. Two vectors that are parallel have cross product zero. So this is zero. Can you tell me what is R cross F? Can you tell me what is R cross F? Well,
It's the magnitude of R times the magnitude of F times the sine of the angle between them.
but what is that? What is this quantity? Is what? The torque. The torque is here, it's defined here. Let's go to It's the torque, okay? It's defined at the beginning. It's the torque. The torque is R cross F. And I have used this torque to deduce that this equation is valid. This is what I did. So what I have proved you now is that the change in the angular momentum per unit of time is the torque. And this is one equation that you have to use. But mainly the equation that you have to use is this one. The sum of all the external torque produced by the forces equal I by alpha. So once that this is understood, we can go to solve examples. So we are going to solve like 8 examples using this equation. So I hope that with 8 examples will be enough to make you understand what is going on here. So let me check that I did not forget anything at the beginning, that I wrote everything. Let me see. Oh, sorry. No, I didn't forget it. Okay. So let's go to the next page. So this is a problem. Imagine that you have a bullet of mass m and velocity v. You have here an object that could be like a cylinder, or maybe can be like a disc, maybe a disc of certain inertial momentum. The mass m, the bullets, will arrive to the object, and in the final situation, the bullet will be incrustated on the object, and the object will rotate. And I want to know, the object will rotate through this axis, okay? In some way, this object is fixed on this axis. The bullet arrived to the object. When it arrives, it's going to be incrustated on the object, and the object will start to move with a certain angular velocity. And I want to find the angular velocity of the rotation of this object. So what is the basic principle here? The basic principle here is this one. The sum of all the external torque equal the change in L divided by the change in time. If the sum of all the external torque is zero, what it means? That the change in L is zero. If the change in L is zero, L final equal L initial. So this is called the conservation of angular momentum. And what it say, the conservation of angular momentum? It say like this: if you have a system with n particles, let's say 2, 3 particles, and there is no forces acting on it, or better, even better, there are no torque acting on it. If the torque is zero, the angular momentum has to remain constant. And this is a powerful theorem to understand what happened in nature. And in nature, for example, when you see a system like the sun and the earth is rotating around the sun. Between the sun and the earth, there is a central force that attracts them. But if you consider the system, the sun and the earth, like a system, the sun and the earth, and this is my system, the earth is going around the sun, and this is my system. And there is nothing from outside acting on the system. There are interaction between the sun and the earth. What this theorem says that you will find the earth with certain angular momentum. You will find the sun with certain angular momentum. But the sum of this angular momentum should be, whatever it happened inside should be constant. So L of the earth plus L of the sun. If nothing is acting on it, the sum should be constant. So L of earth can change. For example, the earth can start to rotate with angular velocity bigger, so L would change. That will mean that the sun will decrease his angular velocity in a way that the sun will be constant. And this is something very, very interesting. For example, I'm going to give you another example. L, I have proved that L is I by omega, where I is the sum of M sub I by R sub I squared. Let's say that you have a guy on an ice on a very low friction floor, and he's skating on this ice floor, and let's say that he do this movement. He opened his arm. And he's rotating a certain omega. Now he do these things. He close his arm. What will happen to the angular velocity? It will increase or decrease. So the angular velocity, the L, is I by omega. The first question that you should ask is, there is something acting on the body? Let's say that there is nothing, that the friction that is here is doing nothing to the body. So when he's open, these have to be constants. So E initial, omega initial, E final, omega final. So when he opened his arm, the moment of inertia increase or decrease? The sum M sub I by R sub I squared will increase or will decrease? For sure, it will increase because now R sub I is bigger. So the inertia, the moment of inertia of this body, the moment of inertia of this body will be bigger. So when he is in this position, the moment of inertia is going up, so the angular velocity has to go down in a way that the product has to be constant. Okay? When you take your arm here, the moment of inertia decrease. So the moment of the inertia decrease. So the angular velocity have to increase in a way that the product have to be maintained constant. So this is what is happening to a skate girl that is skating on the ice. You see the dance that he's making on the ice, and you see how suddenly he increased his angular velocity, and suddenly he decreased his angular velocity. Just opening his arm decreased his angular velocity. Opening his arm increased the inertia, the moment of inertia, so the angular velocity decreased. So what I was thinking is to do this problem. Okay, let's go to do the problem that we have not done yet. So we are going to use, to solve this problem, the following thing. Let me, oh my God, what I have done. Okay, so I'm going to write like this. The system is the bullet with the disk. And I consider the system isolate. So I consider that the sum of all the external torque are zero. And because this is the chaining L divided by the chaining time, this implies that the chaining, the angular momentum is zero. So L initial will be L final. So let's go to count. What is L initial? L initial is the initial momentum, angular momentum of the bullet. The bullet is moving with this velocity. So the initial angular momentum is the mass by the radius by the velocity, because he's going in this direction and he's going to be incrustated on the body at the distant r. So this is the angular momentum of the bullet plus the angular momentum of the disc. But the angular momentum of the disc is I by omega. By omega is zero, so there is no angular momentum initially. Finally, the angular momentum is the angle, both are rotating together with the angular velocity omega, and this is what I want to find. I want to find omega. So the final momentum, L initial equal L final, the final momentum is the final momentum of the disk, that it will be the inertial moment, I, by omega, no omega squared, by omega, plus the inertial moment of the particle of the bullet by omega. Okay? You want me to do it again, this part?
Yes, Professor.
Okay. Okay, this is the disk. The disk is not rotating. L is I by omega. How much is omega? Is zero. So if the disk is not rotating, well, omega is zero. If omega is zero, the L of the disk is zero. Is this understood? Yes?
Yes.
Okay. The bullet is here. The bullet is moving.
Could you repeat that? I'm sorry. If what is zero?
Yes. This is the disk. The disk is not initially rotating. And I know that the angular momentum is proportional to omega, to the angular velocity. What I know is that the angular momentum is proportional to the angular velocity, being the constant of proportionality, the moment of inertia. So if omega is zero, L is zero. So,
Okay, thank you.
so L initial of the disk is 0. Now let's go to see what is L initial of the bullet. The bullet will impact here and will be incrustated here, tangential, okay? And the bullet is at this distance, R. So I'm going to find the angular momentum from this point, from the center of mass of the disk. This is R. And the angular momentum is R cross P, or the angular momentum is R cross MB. And the magnitude of the angular momentum is the magnitude of R by the magnitude of MB by the sine of the angle that forms B with R. So B is going in this direction. R is going in this direction. The angle is alpha, the angle that, and R sine of alpha is this radius R. So the angular momentum R is the radius R by MB. And this is the initial momentum of the bullet. So initially, the initial momentum of the disk plus the bullet. So initially I have MBR. This is my total angular momentum initially. And I say that the principle says that the angular momentum is conserved if there is nothing acting external to the two bodies. And my two bodies are the disk, my system is the disk with the bullet. So what is L final? This is what I'm going to find. L final is the disk with the bullet rotating at certain angular velocity. And I want to know what is this angular velocity that will make the disk with the bullet to rotate. So I will find what is L final. L final is the final L of the bullet, L bullet, plus L inert, or L of the disk. L bullet is a bullet that is moving with certain velocity v and is at the distance r. So what is the angular momentum of the bullet? Is the mass by deposition.
Professor, we can't see what you're writing anymore.
Oh, sorry. Let me. Can you see the? No. Yes. Let me see. Here. Can you see?
Now, yes.
Yes. Okay.
Yes.
This is the final state is the bullet with the disk. This is the axis of the disk, and the bullet was coming with certain velocity, incrustated on the solid, and this is going to rotate with omega. And I want to find omega. And I want to find omega using this equation. The angular momentum initial of the system is equal to the final momentum of the system, final angular momentum of the system. Okay, the angular initial momentum, I see that what's mr by b, the velocity of the bullet. And the final angular momentum of this object that is rotating the disk with the bullet is the angular momentum of the bullet. The angular momentum of the bullet will be at a distance r and moving with certain velocity that I don't know, let's say v. So the angular momentum will be m, v, b unknown, not this b of bullet, by r. Let's go to call this v, b, the velocity. So plus the angular momentum of the disk will be I by omega. But this velocity, the velocity of the bullet that is incrustated, this velocity, they will run together. The bullet and the disk will run together. So M will be omega by R. B will be omega by R. So M R squared by omega plus I omega, I of the disk. So M R squared plus I multiplied by omega is equal to the initial angular momentum, B of the bullet. So the angular velocity is simple M R B the bullet divided by M R squared plus I. Let's say that I is a disk 1/2 M R squared. So this equation will be converted in M R B of the bullet divided by M R squared plus 1/2 M R squared. Okay? And this is the angular velocity of the object. So let's go to another example. Let's go to find another example.
Wait, Professor, could you show that screen again?
Yes, yes, of course, this one.
Okay, thank you.
Okay, let's go, but let's go to do this example. Let's say that you have a disk, and the disk is rotating with certain angular velocity, omega 1. This disk initially is with certain velocity that is 0, it's not rotating. So the disk 1 is going to collide, to have a collision with the disk 2. And I wonder, of course, when there is a collision, there is an internal force between the disk 1 and the disk 2, and between the disk 2 and the disk 1. And the internal interaction that the disks have makes that the disk at the end will be together, rotating at the same angular velocity. So this is a collision between two disks. Initially, the first disk was moving with certain angular velocity. The second disk was not moving, was not rotating, the angular velocity is 0. And I want to apply my conservation of angular momentum to prove that we can find the final angular velocity after the collision. So my equation is Li equal Lf. So what is Li? Is the moment of inertia of the first disk, but the initial angular velocity of the first disk, plus the angular momentum of the second disk. But the second disk, I said that omega is 0, so L is 0. What is the angular momentum finally? In the final state, the two disks are together. So it will be I1 by omega f plus I2 by omega f will be I1 plus I2 by omega f. So this is the final angular velocity that they will have when they collide, when they have the collision and they remain together. They will remain together, not at the angular velocity omega 1 initial, at final angular velocity omega final. And the omega final is related by omega 1 by this equation. So you can find omega f like I1 by omega 1 divided by 2. So this is omega final. This is the final angular velocity. It depends on the moment of inertia of the object that are involved. It's something similar at the conservation of linear momentum. In the conservation of linear momentum, we put Pi equal PF. It's the same equation, but now there is rotation, so we have to use this equation, not this equation. So the other question that you may wonder is the cinetic energy conserved? Well, the initial cinetic energy is not conserved for sure, because when they collide, when they have the collision, they will end it with a common angular velocity, rotating with common angular velocity. But the collision is a collision with when the surface of one disk is making interaction to the surface of the other disk, and that this one is in some way is going to be decelerated by the friction with the disk 2. So this friction will make that the disk 1 will decrease his angular velocity and will make that the disk 2 increase its angular velocity. So one angular velocity will be decreased, the other angular velocity of the disk 2 will be increased, and at the end, both will run together with the common same angular velocity. So the cinetic energy initial is just this one, 1/2 I by omega squared. Is the initial cinetic of the disk 1, because the disk 2 has not angular velocity, so omega is 0. So the final angular velocity, cinetic energy, the final cinetic energy will be 1/2 of the inertial moment, that will be I1 plus I2, plus the angular velocity final square. So if you divide one thing by the other thing, you will realize that the final cinetic energy is lower than the initial cinetic energy. If you divide these things by these things, and you use this equation here, you will find this equation. And because I1 plus I2 is bigger than I1, because I1 and I2 are always something that is positive, because it's the sum of m by r squared. M is positive, r squared is positive, so there is no way that I1 or I2 will be negative. So I1 plus I2 is bigger than I1, so I1 divided by this is lower. So it is lower than 1, okay? This is lower than 1. So the cinetic is lower, or yes, this final cinetic energy will be lower than the initial cinetic energy, okay? So let's go to make another example, Here, I don't know what's going on here. Oh. Well, here what I did is like this. Just to prove you again that the external torque is I by alpha. If you start with L like I by omega, that we deduce at class this equation, I by omega, this is the angular momentum. The change in L will be I by the change in omega. Why I don't take care by the change in I? Because the object is solid, doesn't change the distance. So I remain constant always, because it's a rigid solid. It's a solid that is completely rigid. You cannot change I. I is always the same thing, unless you break this, you break or you stretch, but you cannot stretch the solid because it's rigid. So the change in L per unit of time is I by the change in omega per unit of time. So, but the change in L per unit of time is the torque. And I by delta omega divided by delta t is alpha, the angular velocity. So what I have proved you again, that the external torque is I by alpha. This is what I did here. Okay, let's go. Let's go to do another example. Sorry that maybe I'm giving you too much examples in short time, but we need to finish. We are on the page. We need 3 more examples. Can you, what time is it? It's 2:36. If you are very tired, I can give you 5 minutes to relax. You want 5 minutes to stop here? Maybe I'm running too much.
Yeah.
Okay, I'll give you 5 minutes only 5 minutes, no more. So 2:30, 2:40, let's say it's 2:40, 2:45, 2:45, I'll see you here, okay? And we continue with another example. And I said it's very important that you master these examples, because these examples are the examples that you must know in order to solve all the problems that you have to solve in the book. So please pay attention to this class. Maybe it's a very, very important class for you. Okay, I'll see you in 5 minutes, 2:45. Okay,
Hi, Professor.
hi, everybody's here? Yes? Yes?
Yes, Professor.
Okay, can we start?
Yep.
Yes.
Okay, so we are going to see another example. So this is the first example to apply Newton's law for rotation. Newton's law for rotation. And Newton's law for linear movements. So we are going to apply in this case. Let's say that you have a pulley like this one. There is a rope around the pulley, and we attach at the end of the pulley a mass MB. The mass of the cylinder, let's say this cylinder, this has the shape of a cylinder, is MC. This is the mass of the cylinder. And what we wonder is what will be the acceleration of the body in this case. In this case, we have to use two equations. The equation of Newton's law for rotation and the equation of Newton's law for movement in one direction. So the mass MB will move in a linear movement, so it will not rotate, and the mass MC of the cylinder will move in a way that it will rotate. So the equation that we have to apply to objects that are rotating is not this one, it's this one, the sum of all the torque, because it's the torque that generates angular acceleration. So MB will be the mass of the block, MB from block. MC is the mass of the cylinder, C for cylinder. The first equation of Newton's law applied to the mass MB will say like this. Will say the weight going down, MB by G, the mass of the block by G, minus T. These are all the forces that are acting on the body of MB. The sum of the two forces equal the mass by the acceleration. So this is the first equation applied to the body MB of mass B. The second equation that we are going to apply is to the cylinder MC that have the mass MC. But this cylinder is going to rotate, it's not going to translate, it's not going to move the center of mass, the axis of rotation is here. This axis is not going to be translated. So the axis of rotation is here. So the equation that we have to apply is the equation for rotation. And the equation for rotation says that the sum of all the torque are equal to the moment of inertia by alpha, by the angular acceleration. So we apply this equation. What is the forces that are, the torque that are acting on here? Through this origin O, where is the axis going to your eyes, there is a force here, of course that there is a force. And there is a weight, the weight of the disc here, but through MC by G. But these forces, they don't create any torque. They cannot make the object to rotate. The force that is making a torque is this force. This is the force. And this force is the tension, is the value of the tension. So the torque, the external torque, external to the cylinder, the force that is external to the cylinder is the tension by R, because T by R is the torque. T by R is the cross product of T cross R, of the force cross R, So T by R is the torque, and the torque equal I by alpha. So let's say that you have a cylinder. If you have a cylinder that is not empty, not with a hole, it's a solid cylinder have the inertia, the moment of inertia 1/2 mEr squared. So I will put here m 1/2 mI squared, and I will get that the tension is 1/2 the mass of the cylinder by the acceleration. How do I obtain this equation? I will put I here. I will put alpha like A center of mass divided by R. And I will get that T is this equation. So now I will go with this T, and I will go to the first equation, and I will put this T here. If I do this, I will be able to obtain the acceleration, the linear acceleration. So if I do this, the first equation will be written mb by g minus t, but t I have obtained for the second equation, for the sum of the torque. So will be 1/2 mc, the mass of the cylinder by A, equal the mass of the box by A. So if I regroup this term, I will get that the acceleration will be this quantity. So the acceleration will be a fraction of g. A fraction of g. This is the fraction. And this fraction is less than 1. So alpha will be A divided by R. So alpha will be this same equation divided by R. In this way, I have found the linear acceleration of this body, and I have found the angular acceleration of this cylinder. And the problem is solved. Can we go to another problem, or you have any question here? Oh, this question I like. Do you have any question?
No, Professor.
No? Okay, let's go to the next example. Do you know what is a yo-yo? Have you ever
Yes.
played with a yo-yo?
Yes,
Yeah,
Professor.
Okay, well, this is a yo-yo. The weight will make a torque at this point, and the yo-yo, the rope that is around the yo-yo will unwrap, and the yo-yo will start to increase its angular velocity, and for sure we will have an angular acceleration here of the rotation of the disc of the yo-yo. So what we want to find is what is the tension, and what is the angular acceleration, and what is the linear acceleration of the center of mass. 3 things we can find. So how is this problem to be solved? The way and the strategy to solve this problem is write down the 2 equations. One equation for linear movement, one equation for rotation movement. The Newton's equation for rotation and for linear displacement. So, the equation for linear displacement, sorry. So the equation for linear, for this object, if I apply these 2 equations for this, I will apply the sine external force equal mass by the acceleration of the center of mass. The center of mass is here. Here, the center of mass will be accelerated. The first equation will be mg going down, one force, t going up, another force, and the sum equal mass by this acceleration of the center of mass. Do you see any other force acting on the yo-yo? Do you see any other external forces acting on the yo-yo? No.
Nope.
I don't think so.
That's also the first equation will read like this. The second equation will read like this. The sum of all the torque. So we have to specify the sum of all the torque through this point or through this point. Normally, I suggest you to use the center of mass. Don't use any other point. So I'm going to calculate this equation, the sum of all the torque. Imagine that the rotation takes place through an axis that is the center of mass. So the sum of all the torque, what makes this cylinder to rotate? Well, this force. This force, mg, makes to rotate? No, this force is not creating any torque. The only force that is creating torque is the tension. So the sum of all the torque will be T by R. And T by R will be I, but this I is the I calculated through an axis that is the center of mass by the angular acceleration. But the relation between linear and angular acceleration is this one. So I may use it some places, this relation. So the first equation reads like this, that m by g minus t equal m by a center of mass. A center of mass. So it's the acceleration of this point, of the center of mass. And the second equation reads like this. T by R equal I center of mass by alpha. But if I have a cylinder, if the yo-yo is a cylinder, the moment of inertia is 1/2 m by r squared. So if I substitute this value here and the alpha here, I will get t equal 1/2 ma. This r will go with 1r, this r will go with 1r, t will be 1/2 m by a. So I will take this t and I will introduce on the first equation this t. So I will get mg minus t, but what is t? I already found what is t. T is 1/2 of ma. Just a moment. So I will have mg minus t, mg minus t, t 1/2 ma equal m by a. This is a, also a center of mass. So what we have here is that mg will be 1/2 of ma plus 1 ma. So this is 3/2 ma. So mg is 3/2 ma. So the m will cancel and a center of mass will be 2/3 of g. So the acceleration of the yo-yo under this movement by a rope that you leave it to run, the acceleration will be not g, will be lower than g. It will go down with 2/3 of g. And if you know the acceleration, you know the tension. The tension will be 1/2 m by 2/3 of g. So it will be 1/3 of mg. The tension will be 1/3 of mg. the tension is lower than mg. Okay? So, of course that the tension has to be lower, because the only way for this body to go down, is that the weight should be lower than the tension. Otherwise, you cannot go down. So in this way, this tension is 1/3 or 2/3. I don't remember. Is 1/3 or 2/3? 1/3. 1/3 of the weight. So there is 2/3 going down. And this is the force that is acting on the yo-yo to going down the yo-yo. So is this problem completely understood? There are any details that you want to discuss, or I can go to the next example?
Could you explain, do you see in your second equation where you wrote T times R is equal to the moment of inertia times acceleration?
Yes.
There.
Here.
Could you explain why you have T times R?
Yes, of course.
Is that T for tension or T for torque?
T for tension.
Okay.
The torque is tau.
Okay.
It's a different number, T from tension. So let's go to do it. This is the yo-yo. This is the tension. This is the point of application of the force. This is, I'm going to calculate the torque over the point O, this point O, the axis of rotation. The axis is coming to my eyes in this moment. So what is the torque? The torque is R cross F, is a vector. What is the magnitude of the torque through O? Is the magnitude of R by the magnitude of T, of the force T, by the sine of the angle that form R with T. But R is this vector R, and T is this vector. So it's sine of 90 degrees. So the torque of O is T by R. But this R is,
Oh, okay. Thank you.
this R is the radius, so it will be T by R. Okay? Any other question? Any other question that you may want to ask me? Can I go to the next example? Yes.
I think so, Professor.
Okay. Okay, the next example is a little bit more tricky. This example, is like this. Imagine that you have a cylinder. This is the cylinder. And the cylinder is rotating in this direction. Okay, it's rotating counterclockwise, the cylinder. The cylinder goes through the inclined plane and is going up. So I want to find the acceleration of this cylinder. Of course, that I know the acceleration if the object is not rotating. If the object is not rotating, the acceleration g in this direction will be g sine. This is the acceleration of this object. Is the object does not rotate, it's only displaced. We have done this problem many times during the course, This is the angle theta, this is the object M, the weight is going in this direction. We make these two axes, we project this force over the axis x prime, and we say mg cosine of theta, that is the force through the x prime, equal the mass by a x prime. So the acceleration is g sine of theta. This is the sine and this is the cosine, okay? G sine of theta is the acceleration. So in this way, the object is rotating. So he will encounter a different acceleration. So we want to find the acceleration. The first thing that I want to pay you attention is like this. Why this object over the horizontal surface can rotate? Why? What is the condition for an object on a surface to rotate? What condition must have the surface of the object and the surface of the plane of the floor?
There must be friction.
There must be friction. What happens if there is no friction? If there is no friction,
It doesn't rotate.
yeah, it can rotate, but it doesn't move up in any direction. Do you agree? If the floor
That makes sense.
and the object have no friction, the object rotate, but the object doesn't go up in any direction. It's just rotate and stay here. So if the tire of your car start to rotate and you don't have friction, simple, the tire will continue to rotate and rotate, but you will not move. You will stay at the same speed. If your speed was 0, you will stay at 0. If your speed was 50 kilometers per hour and there is no friction, you will stay at 50 kilometers per hour. So now you are with your car. Now you are with your car and there is friction. These are the tire of the friction of your car, and the tires are rotating in this direction. And as you rotate, you move. So this tire is now here. This distant D is this distant D. And the tire are rotating like this. My question is, who is pushing the car? You are accelerating to the right. Who is pushing your car? What force makes you to move? What
The friction.
The friction. The friction is the force that makes you to move. The second question that I'm going to ask you, what is the direction of the friction? Is it going to the right? Or is going
It's to the left.
Left.
Well, if the friction is going to the left, it's because you are moving to the left. No way a force makes you to accelerate in the direction of the force. The force that makes you to accelerate, not to move, to accelerate in this direction is the force that is M by A, is the force, in this case, the friction force M by A. The force is making to accelerate in this direction is the friction force, and the friction force go to the right.
Are you saying that for only rotational objects or for all objects? Because
No, I'm saying that this is for the case when the tire is rotating on the floor with a static surface, with a static this is some point that is very interesting to understand. Let me explain this. This is the tire. The tire is moving in this direction. Okay? So if the tire is moving in this direction, this point will move with this velocity. This point will move with this velocity. And this point, I'm sorry by the circle, that is not too much a good circle, is moving with this velocity. And this point is moving with this velocity. And the tire is moving and you are here. And you see around you the tire moving, and you see every point moving with the tangent direction. This is the velocity. Okay, now imagine that I'm here. This is the tire, you are here, and the tire is rotating in a very peculiar way. There is a friction force. The tire is rotating in this direction, but the tire rotating with no slippery. What does it mean that? No slippery means like this. This is the radius r. Imagine that you move a distance, imagine this is the point P. The tire will rotate, and when the distance is 2 pi r, means that you have made one revolution, the tire will be here, and the point P will be here. So you have rotate the point P as rotate through this observer one revolution, and at the same time, he has moved this distance in a way that P is still under the same angle, theta, the same angle theta. This is meaning that you travel, you move with no slippery between the floor and the surface. Let's say that the point P stay here, P prime. So this means that there is a slippery and you are not advancing at mass, let's say that the point P prime is here. So you have advanced 2 pi r, but the rotation of the tire has been more distance, have been all this distance. So you have made a slippery, one surface to the another surface. And this is not what it happened when you drive a car. When you drive a car, you drive it in a soft way, in a very nice way, in the way that this tire make one revolution, and this point move the distance 2 pi r long in an x direction. Meanwhile, he has gone one revolution. And this means that there is no slippery. When there is a slippery, you have to go and change your tires very often. If you drive with no slippery, you don't have to change the tires so often. So a slippery, no slippery means that the tire, the length of the tires, you put it here, this length, 2 pi r, and the center of mass was here and now was here. You catch the rotation? So this is no slippery. So imagine that now, and this is something that I cannot prove, but you will visualize. So imagine you are the observer here that are moving with the tire, so you are rotating, okay? So you see, okay, imagine this. Imagine this. This is the observer. The observer, this is a surface with no friction. So you see, you are the observer here, and you see V, 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 and V. Okay? Now I'm here. I'm another observer, and I see this field of vectors V. Now, let's say that I make friction here, and the object is rotating. Now, if the object is rotating, the center of mass have velocity, V center of mass. So this point, the point that is up here, this point, will move at the velocity that he has. What velocity he has? He has omega by r, the angular velocity by the radius. So he will move by the velocity that he has plus V center of mass. So this point now will move faster than before when the center of mass is moving with certain velocity. So if I see things from this observer, I will see that the vector velocity of this point will be the previous velocity plus the velocity of the center of mass. And this point, with what velocity he will move? Respect to this observer, to the observer that is at the center, the velocity that he was observing was this velocity V. But now I'm observing things from this observer. And this observer see how the velocity of the center of mass is moving to the right. So when he see the velocity of the center of mass moving to the right, if this velocity of the center of mass is the same that the velocity of rotation of linear point, but due to the rotation here. So what will be the velocity of this point? The velocity of the contact point between the tire and the floor is zero. That's why the friction that you have is a static friction. If the velocity between the surface of the tire and the surface of the floor is not zero, there is a displacement, a relative displacement with the two surfaces, and the tire will be with time, with very little time, will be spoiled because the surface will be destroyed by the interaction between the surface of the tire and the surface of the floor. Because the velocity is zero means that the friction is static. And the coefficient of the friction is mu static. It's not mu dynamic on this point. Okay? So let's go to do the final problem. This is the final problem. Okay. Another thing, just one more thing before, what happened here? Sorry. Okay, another thing. Let's say that you have this object. Okay? This is the center of mass of this object. The axis is passing through this object. So let's say that you throw this object and now the object is like this. It's the same object. Don't pay attention if I don't draw something exactly similar. And the center of mass is here. There is a theorem that says that the movement of an object can be made. The movement, the general movement of an object is a translation movement plus a rotation movement. So you move your object from here to here. And the object will be like this. Now you rotate the object from here to here. And what the theorem is saying that any general movement can be visualized like a translation of the center of mass plus a rotation through the center of mass. And this theorem is what you can apply, for example, for the tire. You suppose that you have a tire here. And the tire is moving like this, V, V. Now you have here the tire. And now the velocity of the center of mass was 0 here. Now the velocity V center of mass is this. So the velocity of this point, let's say that the velocity of the center of mass, not to make complicated, is exactly the same as V. So let's go to erase here, not to put it like this. And the velocity of the center of mass will be, let's say, same like this velocity, the same vector in the same direction than this vector with the same magnitude. So this vector will be like here. And this vector will be 0 velocity. And this is what is happening, that you translate the object and you translate the center of mass, you put velocity to the center of mass, and the translation plus the rotation make this figure again. So let's go to solve the problem. You will get a better idea of what I have said here. So the problem is like this. Wow. Shh. Let me put it smaller. Okay, see, this is the problem. This is the problem to make. Let's say that you have the inclined plane. Let's say that the object is here, is moving with certain velocity v0 and is rotating. So what it means that? It means that the center of mass of the object has velocity v0, and meanwhile the center of mass has velocity v0 is rotating. So it means that the velocity of the point, of this point, is also v0, the velocity rotating. Indeed, the velocity is 2v0 respect to the external observer. Respect to this observer will be only v0, but respect to this observer will be the velocity of the center of mass plus this velocity. This vector will be 2v0, 2 times v center of mass. So in this way, he can rotate without a slippery. No slippery, no. This point will have velocity 0. So he's rotating and he goes up. And when he goes up, there is an acceleration that makes the body not to rotate and not to translate. There is an angular acceleration that prevents you to rotate, and there is a linear acceleration that prevents you to go higher. So we want to find this angular acceleration and this linear acceleration. So let's go to find using our principle. The first thing that I have explained is that when this is going up and this is the rotation, is in this side, the friction is going in this direction, I think. Let me think. Yes, it's going in this direction. There is no way that you can accelerate. But even if I make a mistake, the equation will tell me that it makes a mistake with a sign. Let's go if the equation tells me that there is a mistake. The first equation is the sum of all the external force What time is it? 3:25. Okay, let me finish this problem and the class is over, okay? Okay?
Okay, Professor.
Yeah. Okay. So the first equation says that the sum of all the torque is the mass by the center, by the acceleration of the center of mass. And the second equation says that the sum of all the torque through the center of mass, through this point, is the inertial moment of the center of mass by the angular acceleration. If I apply the first equation, I will have friction going up, mg sine of theta going down, mg sine of theta going down, equal mass by acceleration of the center of mass. Do you see any other forces in this direction? Do you see any forces in the parallel direction to the plane? I see the friction and I see the component of the weight in this direction. Okay? Is this first equation?
Yes.
Okay, so now you are tend to use this equation. The friction force is the mu static by the normal. You cannot use this equation. I'm going to explain you why you cannot use this equation. Because you don't know what is the friction force. Because the friction force works like this. When you have a body and you apply a force like this, the friction force will oppose, the static friction force will oppose in a way that at the beginning you cannot make the body to move. When you increase the force, the friction force increase. So which friction force is this one or this one? You don't know what is the friction force, if it's here or if it's here. So you cannot use this equation. So we use the second equation. The second equation says that the sum of all the torque is the moment of inertia through the center of mass by the angle alpha. So what is the torque? The torque, the external torque. Who produces external torque on the disc, on the cylinder? Well, the only torque that produces on the cylinder is not the weight. The weight doesn't produce any torque because it's applied directly to the center of mass. The one that is making torque is the friction force. And the friction force makes a torque that is Fr by R. And I put a negative sign because the torque will be counterclockwise. And it will be clockwise. And clockwise is negative torque. Counterclockwise is a positive torque. So I put it here like this. So the torque will be minus Fr by R. And the sum of all the torque equal I center of mass by alpha. I center of mass, okay. I center of mass is 1/2 m by r squared. The angular acceleration is the acceleration of the center of mass divided by r. This r goes with this r, and this r goes with this r. So I will get the friction force minus 1/2 m by the acceleration of the center of mass. So I will take this friction force and I will go to my first equation. The first equation says that the friction force minus mg sine of theta equal m by the acceleration of the center of mass. So I will take the friction force, I will put it here, and I will have minus 1/2 ma center of mass minus mg sine of theta equal mass by the acceleration of the center of mass. I will reduce this and I will find that the acceleration of the center of mass will be 2/3 g sine of theta. For a cylinder, we have inertial moment 1/2 m by r squared. If you change the object and you put a sphere, for example, instead of a cylinder, the sphere has another moment inertia, and this value will change. So in this way, I have found the acceleration of the center of mass. And A is equal alpha by r. So the angular acceleration of the object will be A by r, A divided by r. So this divided by r is the angular acceleration. So these are the problems that I consider you should know how to solve. There is one thing else that I don't want to forget, that is conservation of energy. Let me finish with this, and I promise I will not do. Oh, there is one example more here. Oh, this one. Let's go to do this. Example, conservation of energy. This is a very useful technique to solve problems. Let's say that you have this system. The system is a pulley with mass mc, the mass of the cylinder, and a mass, the block, mb. This is the mass of the block, okay, the mass of the block, mb. So let's say that you are in this position, in this state. The state where the cylinder is here, the mass is here at certain height, and you want to know what is the velocity of this mass mb when it arrives to the floor, when he's here, when he has displaced the quantity y0. What will be the velocity when it has arrived to the floor? And the way to find the velocity is to make conservation of mechanical energy. And the conservation of mechanical energy say, make the mechanical energy at the position A and make the mechanical energy at the state B. And this mechanical energy is the mechanical energy cinetic of the body 1 plus potential of the body 1 plus cinetic of the body 2 plus potential of the body 2. And you make this equal to the same thing in the state B. So let's go to do this equation. Mechanical energy equal mechanical energy at A, at B. So what is the mechanical energy at the state A? The state A is when the mass is here, and the cylinder is here. The state A have cinetic energy of the cylinder 0. There is no rotation. There is no translation of the cylinder. So for the cylinder, all the cinetic and potential energy is 0. Well, you can put potential energy of the cylinder like mc g by h, at this h. But you will have to put it inside mg by h because it's something that that will not move because the cylinder will not move his center of mass. So the potential energy of the block will be m of the block by g by 1. In the final state, you will find the object with mass mb moving with certain velocity v. So having a cinetic energy like this, having 0 potential energy because it's arrived to the floor, and on the state B, the cylinder is rotating, so it's having certain amount of cinetic energy, and this is the cinetic energy of the cylinder. So if you relate V of the block with omega by r, you will find that the velocity of the block B is this one. So this is a very powerful method to solve equation, to evaluate at the state A, the kinetic energy and potential energy of all the bodies involved, and to make it equal to the kinetic energy and the potential energy of all the body involved. And with this, you get a relation that it allows you to obtain, for example, in this case, V sub B. So you can obtain V sub B in terms of the mass of the block and the mass of the cylinder on G and the height I sub 0, initial height that it was. So so the class is over. I have shown you what I want to show you, and I hope you have
I'm getting like tax return.
so
Professor,
Getting
could you
like
mute
tax
everyone?
return.
questions.
Yo, mute your mic.
Could you
Can
mute
you
everyone?
mute?
Sorry?
Can you mute everyone first?
Yes, I can hear everyone. Yes.
You don't have to stop. Up to a year.
Can you mute everyone?
Can I mute everyone? Yes, of course that I can mute everyone. Let me see. Wow.
Oh, Professor, could you go back to your screen so I can take a screenshot?
Yes, just a moment. Let me see what happened here. Oh, yes, let me silence everybody. Okay, now you want me to share my screen again? I will share. Okay.
Professor, now can I tell you about my quiz?
Professor, the screen isn't correct. It's not on.
I'm trying to do it. Just a moment.
Oh, okay. Sorry.
Yes, let me try. Screen mirror. ¿Por qué no sale aquí screen mirror? A ver. Aprieta acá. Deja ver. ¿Verdad? Ahí está. No, aprieta, no aprieta. Okay, now, yes. Okay, questions?
The screen is blurry. You need to select the screen.
Oh, it's not working, the screen?
It's
Just click on your iPad. Just click the iPad screen, and then go back to the.
Is it now?
No.
No, pa.
There.
there. It is. Thank you.
Now you can see.
Yeah.
Okay, so we start with questions. So the test, I have prepared for you quiz 6 in order you to use quiz 6 to try to review what I have said and to make examples similar question that makes you to refresh and to think about this subject. So please take the quiz 6. The time to take the quiz 6, if you want, I will leave it open until Thursday. Would you like this? It will be easier for you and you will not be under so much pressure.
That would be amazing, Professor.
Okay, I will do it like this. Let me repair it before I forget. So quiz 6 is going to be open at 4 p.m. You can take any time before 4 p.m. and And Thursday, quiz 6. Quiz 6, you can take it anytime. Let me pour it. So anytime before the between today and let's say 11 p.m. of 11 a.m. of Thursday, can be.
Yes.
Okay.
Thank you, Professor.
Okay. So let me see. Put it here, not to forget. 11 a.m. on Thursday. So a.m. Yeah. So the test 2 will be on Thursday at 1 p.m. Right? So I was thinking to make 8 problems. To choose like 5 easy questions for you, and 3 questions more delicate, more subtle. So you will find the test 2 all will be multiple choice, and you will find the 5 easy questions that I consider easy, and 3 questions that they are not very difficult, but they are not so easy, not so direct. So what else you need to know?
Oh, Professor, you know the homework that you posted that has like 11 problems?
Yes.
That homework doesn't have a submission button, so I'm not able to submit my homework.
Well, let's go to repair it at once.
And that's 6.9, Professor.
6.9, thank you. Thank you.
6.90. 6.9 doesn't have any problems.
6.90.
Yeah, Professor, it's 6.90, not 6.9.
I know. Okay, I'm sorry that I forgot to put the submission. File upload. It's done. Okay?
I think there's also a couple other ones that don't have it either. I think like 5 point, the last one in unit 5.
5 point what? Sorry?
And in unit 5, I believe there's one that doesn't have a submission button. 5.9?
5.3, 5.4,
5.9.
5.9. Wow, I made the mistake. Wow.
It's okay.
It has the submission, eh? It has. 5.
Yeah,
It has.
that one has it, and that was due yesterday.
Oh, that's why it closed. My bad. Wow.
Until July 27th, I'm going to put it until the 30, okay? So
Okay.
I'll give you time to make the homework.
Okay, that's nice. Thank you. I appreciate that.
Okay.
Hi, Professor. I have a question about the exam.
Yes.
Do you know if it will be on every unit or just the more recent units?
The problem will be concentrate mainly on Newton's law, work and energy, and rotations. But of course that the course is designed in a way that you need to know the cross product. So this is for unit 1. You need to know vector velocity. This is for unit 2. So at the end, you need to know tangential acceleration, normal acceleration. So the problems that you will find are problems based on unit Newton's law, based on work and energy, and based on rotational motion. These are the examples.
Thank you, Professor.
Question, I think. Maybe there is one question that is specifically from unit 2, maybe, but only one question I think it will have. No, I will focus on the last 3 units, okay?
Okay, and you said that the test was going to be 1 p.m., not 1:30 p.m.?
Oh, sorry, 1:30 p.m. starting 1:30 p.m. with lockdown, and similar as we did the last test, okay?
We need to be on Zoom?
Yes, similar or exactly the same as before as test one. You need to be on Zoom. I will be with you answering any question if you have any question about the exam. If there is any things about grades, I will appreciate if you can wait until Friday, because I hope on Friday I will have all the grades, including test 2, so I can chat with you and we can see your grades if you want to see your grades, okay? And there is on grades, there are a column, the first column, if you go to grade, there is a column that is say notes. I was planning to put something on the notes that will say you your grade, your letter, or the sum of all the points that you have in a way that you can calculate easily. And with this, if you think that there is something wrong, you can call me, we can review the detail one by one. And this is what I was thinking, because you know what happened on Canvas, there is a grade book, but I'm not sure if the grade book makes the calculation correctly. So because I'm not sure if he makes the calculation correctly, my plan is, that's why I'm asking you to talk to me on Friday. My plan is to export all the data to an Excel sheet, to work the Excel sheet with detail, to give you the final grade on Friday. I think that I will be able to give you the final grade. And so I will have all the information already export to Excel, and I can tell you exactly what's going on with your grades. So if you please, if you wait until Friday, it will be wonderful.
But Professor, I think the semester already ends on Thursday.
Sorry?
No, they had their grading period. Their grading period goes on until like August 5th. So don't worry.
No.
Then how would we meet if all we have is one more Zoom meeting on Thursday? Would he make another Zoom meeting for Friday specifically?
Of course. You will have to contact me on Friday to review your grades. Of course.
Okay, how do we contact you? Through email?
If you want, you can make a schedule appointment for Friday, maybe in the afternoon, to give me time in the morning to finish. Maybe, or maybe on Sunday. Sunday will be more safe for me, to be sure that I have everything, all the information. So maybe on Sunday we can have a meeting for those students that need to talk to me. Maybe Sunday, what time will be good for you? 11 a.m.?
Yeah, 11 or 12 in the afternoon.
11. So on Sunday, 11 a.m., I will have all your grades, everything, all the details. If I made a mistake, I'm more than willing to correct it. But you have to tell me what is the mistake, because sometimes I don't realize what is the mistake, no? So I've been working all the data. I can show you the data one by one, so you can analyze if you consider that there is something wrong. You ask me for all the data, all the detailed data, and you review by yourself the data. And on Sunday, I will have the final grades. And on Friday, I hope I can write something on notes to tell you approximately the grade that you have. And if you consider there is something wrong, please make the appointment for Sunday. and we will review it. Okay? It's
Perfect. Thank you.
it's well like this.
Yes.
Yeah, that sounds fine, Professor.
Okay. So
Professor, if we have any questions regarding the content before the test, what is the best way to contact you? Like email or through Canvas?
after the if you have a question after Sunday, you mean?
No, a question like now that we're gonna be studying for Thursday.
Oh, you can contact me anytime. I'm here. I'm at home. I'm not going out.
Is email the best way to contact you?
Yes, email me and we will fix an appointment or whatever we need to do. Okay.
Awesome. Thank you.
Zoom link on Sunday, correct, Professor?
Sorry.
You'll send us a Zoom link for Sunday?
This link, the same ID, the same ID that you use for the class, I will be connected at 11.
Okay. And how long will you be there for? Until 12 or 1?
Well, if there are no students, I will go for lunch. If
Okay.
there are students,
I'll be there at 11.
from 11, I'll be on Zoom.
Okay.
Okay. Okay, anything else?
Nope.
Okay, so
Professor,
yes.
what if we're unable to make it to the meeting on Sunday?
Well,
But like, I would like to see what my grade would be.
yes, you send me an email and we make another appointment for Monday, 11 p.m. So we make 2 appointments. Sunday, 11 p.m. I will be on Zoom, and Monday, 11 p.m. I will be on Zoom.
You mean AM, not PM.
Yeah, sorry, yeah, sorry. Okay.
Okay.
So if you cannot catch me on Sunday, you can catch me on Monday, or you can send me an email. And I prefer you don't send me an email. You just appear on Zoom at 11 or 11:10, and that's all. It's easier. Okay. Any more questions? Any more questions? Sí. Okay. So can I close the meeting? Can I end the meeting?
Yeah.
No more question, right?
No, thank you.
Okay, thank you. Bye-bye.
Thank you.
Thank you, Professor.